In this video, we're going to talk about the greatest integer function. Now, the greatest integer function is defined by saying that this notation here, with x in these brackets, denotes the largest integer that is less than or equal to x. Okay, let's look at an example. Find, in part A, the greatest integer less than or equal to 7.3. Well, another name for integer is whole number. So what's the largest whole number or integer that is less than or equal to 7.3, and that would be 7. Okay, what is the largest integer, the greatest integer less than or equal to pi? That would be 3, right? Because pi is 3.1415, and so on. What is the greatest integer that is less than or equal to 5? Well, since we have the or equal to, and 5 itself is an integer, the greatest integer less than or equal to 5 is 5. Now in part D, be a little bit careful. The greatest integer less than or equal to negative 4.7 is not negative 4. Okay, it's going to be negative 5 because we're looking for an integer that is less than negative 4.7. Okay, and that would be negative 5. Okay, let's sketch the graph of the greatest integer function. Now notice if we take any number that's between 0 and 1, okay, on this interval between 0 and 1, the greatest integer less than or equal to that number would be 0 itself. So it would have a height of 0. For any number that's between 0 and 1, the graph is going to look like this. And in fact, the greatest integer less than or equal to 0 itself is 0. Okay, now any number that's between 1 and 2, the greatest integer less than that will be 1. So we go up to a height of 1. Okay, and the greatest integer is going to look like this. Now what about at 1 itself? What is the greatest integer less than or equal to 1? It's 1. So we're going to have a filled in circle here. This one will be an open circle there. Okay, and then the greatest integer, if we take any number that's between 2 and 3, the greatest integer less than or equal to that would be 2. So we go up to a height of 2. Okay, for example, if we take the point 2.7, the greatest integer less than or equal to 2.7 would be 2. So I'm plotting the point 2.7 comma 2. Now at the right end of each of these line segments is going to be an open circle, and at the left end is going to be a closed circle. And the graph is going to continue like this in both forever. Okay, kind of like steps right here. Now if we take a number that's less than 0, so between -1 and 0, then the greatest integer less than that number would be negative 1. For example, what's the greatest integer less than or equal to negative 0.6? It would be negative 1. So any point that's in this interval is going to have a height of negative 1 down here. Now 0 itself, the greatest integer less than 0 will be 0, so that's up here. And the greatest integer less than or equal to -1 will be -1. So again, you're going to keep continuing these steps here. Okay, so this is what the greatest integer function looks like. Notice that it passes the vertical line test. Okay, any vertical line you draw is only going to intersect the graph at most one time. Even a vertical line right here at, for example, 2 would cross the graph here, but it would not cross the graph here. Okay? Okay, now notice these look like steps here, and in fact functions whose graphs resemble this function, this greatest integer function, are called step functions. Okay, and you might think, what does this have anything to do with actual real-world situations? But we're going to do an example here of a real-world problem where the graph of a function that we get looks like a step function. Okay, it is a step function. So let's read the example. It says an overnight delivery service charges $30 for a package weighing up to 2 pounds. For each additional pound or fraction of a pound, there is an additional charge of $3.50. Okay, let d of x represent the cost to send a package weighing x pounds. Graph d of x for x in the interval 0 to 7. Okay, now I've put a scale on each of the axes. On the vertical axis, we have the cost in dollars, and on the horizontal axis, the x-axis, we have the weight in pounds. So notice, how much does it cost to for a 1 pound package? Okay, what is the cost for a 1 pound package? Well, it's $30 for a package weighing up to 2 pounds. So anything up to 2 pounds, it's going to be $30. Okay, so if it weighs 1 pound or 1.7 pounds, it's going to be $30. Now, for each additional pound or fraction of a pound, it's going to cost an additional $3.50. So anything between 2 and 3 pounds, okay, is going to cost $33.50. Okay, $33.50. Okay, now if it's 2 pounds exactly, it's just going to cost $30. Okay, so this is going to be an open circle here. The closed one will be down there. But if it's anything up to or including $3, it's going to be $33.50. Okay, if you have a package that's between 3 pounds and 4 pounds, it'll cost an additional $3.50. So it'll be $37. Okay, so we can draw in this. Notice that if it's 4 pounds, the package will cost $37, or if it's 3.8 pounds, it'll be $37, or 3.1 pounds, it'll be $37. Now 3 pounds, it'll be down here at $33.50. Okay, and I drew in the rest of the graph the best that I could. So notice that every time it goes up a pound, it's going up $3.50. Okay, but for any package, for example, that's between 5 pounds and 6 pounds, it's going to have the same cost. Okay, the same cost. In fact, you can figure out what that cost would be exactly. It's made 1, 2, 3, 4 steps up from $30, and 4 steps of $3.50. 4 times $3.50 would be $14. So any package that's between 5 pounds and 6 pounds would end up being $44, right? 30 plus the 14, okay, it'd be 44. So for example, 1 point on this segment here would be 5.3 comma 44. Okay, so this graph is a step function, and you can see that these step functions do arise in actual real-world situations.